In this short video, let us see how we can define the Lebesgue integral of a function not necessarily defined on an interval but an arbitrary measurable subset of the real line. The definition is very straightforward and various properties of the Lebesgue integral will transfer to these general Lebesgue integrals on arbitrary sets quite easily. Let S subset of R be a measurable subset, be a measurable set. Let f from S to R be a function. Define the new function f tilde of x, which is by definition going to be equal to f of x if x is in S and 0 if x is in R minus S. So we are essentially extending the function f by setting it to be 0 outside of its domain of definition, which is the set S. Now we say f is Lebesgue integrable on S if f tilde is Lebesgue integrable on R. Furthermore, we set integral of f over S to be by definition the integral over R of f tilde. So the definition is rather straightforward. We just extend the value of the function f by 0 outside the set S, and then we define the integral of the function f on the set S to be that of the integral f tilde on the whole of the real line. Some immediate consequences which I am going to leave it to you to show, they just follow in one line from the definitions, are the following. Remark: if T subset of S is measurable and f is Lebesgue integrable on S, then f restricted to T is Lebesgue integrable on T. Rather straightforward property. And the second property is also equally expected and equally trivial to show. If S has finite measure, then the integral of the function 1 on the set S gives you mu of S. The measure of S can be obtained by integrating the function 1 on the set S. This is almost just by definition. One slightly little bit more involved theorem, which again I'm going to leave it to you because the hard work has been done when we prove the corresponding property for measures, is the countable additivity property of the integral. So let AI be a countable collection of pairwise disjoint subsets of pairwise disjoint measurable subsets, disjoint measurable subsets of R. Let S be the union of AI. Then of course S is measurable, which is just a consequence of the material we did in the last video. Then S is measurable if f from S to R is integrable, that is f is in L of S, then f restricted to AI is there in L of AI. So each restriction is Lebesgue integrable, and we have integral of fs is just summation integral of f over this ai running from 1 to infinity of f restricted to ai. Okay, so the obvious thing that you expect holds provided the sets ai are all pairwise disjoint. there is a converse also. For this conversely, suppose each f restricted to ai is an L of ai and the RHS above converges, then f is an L of s and the equality above holds. So this theorem is more or less just a trivial consequence of the countable additivity of the Lebesgue measure. It's straightforward to prove and it's an instructive exercise for you to check whether you have understood the various definitions to prove them. Now let's move on and also define the Lebesgue integral on complex valued functions, and there's really nothing going to happen there. The definition is utterly straightforward and exactly what you would expect. Let f from I to C be a function. We say f is Lebesgue integrable on I if writing f equal to u plus iv, we have u comma v are both Lebesgue integrable on I. We define integral of fi to be nothing but the integral over I of u plus I times integral over I of v. So we just generalize in the most obvious way. In a similar way, we say f is measurable on the interval I if u comma v are both measurable on the interval I. Okay, now one easily checks that some scalar products etc. of complex measurable functions are complex measurable furthermore observe that mod f is u squared plus v squared the whole power half. So from what we have established, if f is measurable on I as a complex valued function, then mod f is measurable on I as a real valued function. This is because the function, whenever you compose a continuous function with two measurable functions, then what you end up with is still a measurable function. Because of that and because of this expression for mod f, we immediately get that mod f is also measurable. So these are all straightforward to show. Moreover, linearity and other basic properties of the Lebesgue integral hold true for complex integrable functions also. And the proofs are nothing more than just writing f equal to u plus iv and applying the same results that hold in the real case for both the integral over u part and the integral over v part. Since the integral of f is just defined to be integral of ui plus integral of I times integral over capital IV, you just apply the corresponding results for both this u and v part and you're done. There's really nothing much to do. Only one new result we have, I mean, it's not a new result. You cannot just get it straightforward from the real case. There's a little bit of work to be done. So let f from I to c be complex integrable, complex Lebesgue integrable. Then the absolute value of the integral is less than or equal to the integral of the absolute value. We have already established this for real valued functions. Now we are going to establish for complex valued functions also. Here a little bit of work is involved. So first of all, if integral of if is just 0, then nothing to prove. So assume integral of if is some r e power I theta. So here I'm going to borrow a basic fact from the theory of complex numbers, which you would have definitely learnt in your high school. Any non-zero complex number can be written as r e power I theta. This is the polar representation of the complex number. Here r would be the absolute value of that complex number, and theta is the argument. So this is just a basic fact that you would have no doubt learnt when you studied the basics of complex numbers. Okay, now what you do is consider e power minus I theta integral if. Okay, this is just r, which is integral over if, the absolute value. Okay, now by the linearity of the Lebesgue integral, which we have not shown for complex valued functions, I invite you to provide a proof. As I said, these follow immediately from the fact that the integral of f is defined in terms of the integral u and integral v. So from that you can get the linearity. So you can write this as integral over I e power minus I theta f. Okay. Now this is going to be the absolute value of integral of if from what we have, just from the definition of what this theta is. Now if you write this as capital U plus IV, these are U and V are real numbers. Okay. If you, or rather don't do that, if you write e power minus I theta f as capital U plus IV, where U comma V are in L of I, real valued integrable functions. Write it like that, because integral of I e power minus I theta f is real valued, we must have integral of e power minus I theta fi to be nothing but the real part of the integral, which is just integral over iu. That is, in other words, what I'm trying to say is this other term which is there plus I times integral I of v, this is actually 0. This term will not play a role in what is to come. Just that integral iu, that will be the non-zero term. Okay. Now this is less than integral over I mod u, simply because of the ordering property of the Lebesgue integral, and this is going to be less than integral over I of modulus of e power minus I theta f. This is simply because e power minus I theta f is u plus iv. Okay, and by the basic property that the real part, the absolute value of the real part of a complex number is less than or equal to the absolute value of the complex number itself. Okay, excellent. We have this. Well, e power minus I theta, this is a unimodular complex number, so this is equal to integral over I of mod f. Okay, and now we immediately get what we wanted, because the left hand side is just integral over I mod f. So this proves this inequality, that the absolute value of the integral is less than or equal to the integral of the absolute value. So this concludes this short video on Lebesgue integrals on arbitrary subsets and some properties of complex valued Lebesgue integrals. This is a course on real analysis, and you have just watched the video on Lebesgue integral on arbitrary subsets.